Peter Lumsdaine?
Lumsdaine.
Lumsdaine. Sorry, I'm you're Russian. Peter Lumsdaine, currently from the University of Stockholm, and Peter will speak on coherence issues in models of types.
Thank you very much. So, yes, hello. This is one of those talks which, as often I should start with a slight apology that for some of you who have heard me talk about this before, in this summer and also last summer, but I have, I hope, several new things, but I have at least one thing that's definitely new to anyone, which is that finally the work that this is mainly based on is now an actual paper that's actually publicly available. So this is based on archive 1411.
Well, that says it all, really. You might as well stop now.
Thanks very much. So this is joint work with Michael Warren, one of my several academic brothers, another student of Steve's who's in California at the moment, and the title of the paper is more specific than the title of this talk. It's about the local universe model and then this talk is also about other coherence constructions in dependent type theory. So, before telling you what any of these coherence constructions are, what do I mean by coherence? What are we trying to construct? What's the thing that we're trying to do? What's the problem we're trying to solve? The problem with that has come to be called the coherence problem is an issue which arises when you try to make models of type theory. So you want to give models of type theory by specifying something along the lines of, say, model types as vibrations in, let's say we're doing some special set model. We'd say model types as vibrations in some special sets. Terms as morphisms or sections or something. And then for each logical constructor, you want to give a corresponding construction in vibrations. So, say model pi types by the pi functors between the slices of simplicial sets. Model identity types by path spaces, and so on. So you want to specify your model by saying, here are what we're interpreting the basic things as, and here are what we are interpreting each logical constructor as. And then you want this, when you give this data, you want to be able to say, okay, so that automatically extends from little interpretations of the individual constructors, one can inductively extend that to an interpretation of the whole syntax. So extend this automatically to the whole, so to an interpretation of the whole syntax. And that's exactly how it does work in the end. So how does this sort of automatic extension work? This automatic extension works by appealing to a universal property of the syntax. It's appealing. So this extension universal property of the syntax. You're saying we've got certain algebraic structure, and then whenever we have some stuff with this algebraic structure on, then automatically one gets a function defined on the whole of the syntax coming into it. In other words, one is saying that the syntax forms an initial object which we'll generally call C sub t for the type theory, in some category which I'll call strict models of T. And this is what one does, but there's a wrinkle that usually comes up, in that very often the actual things that you wanted to start by talking about don't really form something in this category. If these things usually did give you an algebraic structure like the one in this category, then you're golden. And sometimes they do, and that's good. But sometimes they don't. Often, what you first get is some weaker algebraic structure, which let's call for now, a weak model of T, which, this is a bad name, this is a terrible name, because one shouldn't really, or at least, no, plenty of people have said it's a fine name. I would be in the camp that feel it's not a good name, that to justify calling it any kind of model, one needs to know that one can get a model in the sense of a function defined out of the syntax. So I'm calling this as a placeholder, where this is not saying it's justified yet as a model, that these are the things that we will try to justify as models as we get into the coherence constructions. So this name is not justified yet. So in what sense does this usually end up weaker? In what sense does it need to be strict? Typically, the algebraic structure that this category is the category of, the algebraic structures that correspond to strict models of syntax have a lot of equalities. Have a lot of equalities which will not hold in the weaker models. And especially, but not only, but especially equalities between the things which will represent types or objects. So this is again the idea coming up which we saw in Benedict's talk, that it's typically unnatural in mathematical settings to talk about equality between objects, and yet, unfortunately, the syntax itself does have equality between the expressions that represent types, and so in setting out its straightforward universal property, one has to then talk about equalities between the things you're interpreting those as. But it's not just equalities between those once one gets to the homotopical models, because again in homotopical settings it's somewhat, not entirely, but often somewhat unnatural to talk about strict equality between elements of objects as well. So for instance, morphisms in a higher category, it's somewhat unnatural to talk about equality between again. And so in also between morphisms. And so, the coherence problem is to bridge this gap, that the way we want to construct models doesn't quite give us the things that it's really fair to call models. So the goal of coherence constructions bridge this gap so if we've got the if we have the weak models of T, and we've got some weak model of T that we built, something which has stuff which looks like it kind of sort of ought to be a model of T, but doesn't quite satisfy all the strict things, well, then we find some strict equivalent to it, some C primed, which let's call the strict replacement of C. And so over here we should have some kind of equivalence between C primed and C. It might be a morphism in one direction or the other, it might be a span, but it should be something that's sort of some reasonable kind of equivalence. And then, since this is a strict model, we get our map into it from the syntactic category of the theory, so that gives a genuine direct interpretation in the most immediate sense there, and then bring that back down into the weak world, we now at least have some kind of way where, by composing with this equivalence somehow, we can get a slightly less strict, but some kind of an interpretation of the whole of the syntax in C itself. So this is the big picture of the setup, and now I have the other thing which I hope for those who saw this talk earlier in the summer will be new, in that time I said a lot more about the big picture, and came out at the end to giving a bit about the details. Today I'll go backwards compared to that. I'll start at the details and work up to then try and fit into the big picture. So, yes, let me keep on this board for now. So, I want to set up now what the strict and weak model will be. So, the basic setting for models that I'll use is comprehension categories. I should say, let's say, formalism, not setting. So I'll use the comprehension categories here. There are a lot of options on the market of different formalisms you could use. Several of them first set out by people in the audience. So the others include categories with attributes, categories with families, contextual categories, and the comprehension categories are slightly more work to deal with than all of the rest. And the payoff for that price is that they generalize better to the weak models. These, so as for the strict models, any of these would do very nicely. For the weak models, the comprehension categories are set up to be a little more general than the rest. So, comprehension category consists of data C, chi, and chi, where C is a category, chi is a fibration over C. So, Growth and deep fibration, say, and if that's not familiar, I'm not going to define it, but I will go over roughly what it means in a minute. And then chi is the map called the Comprehension, which goes from types into arrows in C, and meets with the codomain functor. So chi is a Cartesian functor, and this triangle commutes strictly. So, what this means is that C we think of as the category of contexts. Oh, sorry, I should say chi also seems to be full. Sometimes one considers the generalization where it's not, but for today it's always full. So C we think of as the category of contexts of
Sorry, do you mean fully faithful?
Yes. Thank you very much. So C we think of as the contexts of the type theory. Then, being a fibration, roughly what that means is that for any object of C, we have the fiber of that fibration is types over gamma. Think of as types in context gamma. This is a category and for each gamma, and we have for any map in the base, which you think of as a context morphism, a substitution between contexts. We can substitute between types, so can pull back types over gamma to types over gamma prime. And this is pseudo-functorial in F. So it's functorial up to coherent isomorphisms in these maps F in the base. So if we pull back twice, that's not necessarily exactly the same as what we got by pulling back once, but it's isomorphic to it, and these isomorphisms fit together nicely. And that's what's encoded neatly by the definition of a growth and deep fibration, which packages that up nicely. I should say, for those who are caring a lot about it, yes, I think of all fibrations as being cloven, so...
Benaboo would shoot you.
Yes. But he's not here.
But he's not here.
Thomas Streicher would also complain, but I don't think he's here either. So, but I will be, so I'm treating this cleaving as not, so I don't want to call it a cloven fibration, because the maps, we won't care about them preserving the cleaving. I would think of the clovenness as, it's just like we're saying an existence condition, but we're reading that existence condition in the constructive tradition as being witnessed by something which will then never do anything that depends on. Except we will do things that depend on it. But we'll kind of confess about that at the time. So
This concept, sorry, we just defined like the notion of comprehension category without any references to things like quasi vibration. But so to define it as an elementary concept. Directly kind of in Fault's style of, well, not exactly Fault, but in a style you could do that.
So you certainly could do that.
With dependent type.
Absolutely could do that. For now I'm saying this
Might
just for conciseness. Certainly, I don't know about nicer for the general case, but certainly for the next thing I'm about to say, it would be nicer to define it individually as a multi-sentence algebraic structure, which is that oh, actually, sorry, no, I should say just a moment, before going to that, one more thing to say here, which is what the comprehension does So if we've got a type over a context gamma, then we can extend the context, and we denote the extended, and so chi, it takes something in here to an arrow whose codomain is the same thing over here. So we've got some arrow into gamma, and we write its domain as gamma.a, think of it as a context extension, and the Cartesianness of chi as a functor says that substitutions get taken to pullback squares. And the thing so this looks like it's describing a type theory in a lot of ways. The one obvious thing a type theory has that we haven't mentioned yet is terms. But terms, so we're seeing this as the dependent projection context morphism that just forgets the variable of type A, and then a term then corresponds to a section of that morphism. You've got things from gamma, and you want to get a context morphism to gamma.a, which on all of gamma is just taking the variables and not changing them. Then the one remaining thing to give is a term of type A. And so think of terms of type A over gamma as sections of this dependent projection. Now, this is roughly corresponding to the type theory, but of course, if we got this from syntax, and then we're implementing the pullback between fibers as syntactic substitution in for the variables of the context, then of course that is literally on the nose functorial in context morphisms. If you perform the identity substitution, you literally don't change your type. If you substitute in and then substitute something else in, or compose these first and then substitute, you really can't tell the difference in the syntax. And so a comprehension category is split if chi is a split fibration, which means that you've got a particular cleaving for which its pullback maps are strictly functorial. And this corresponds to the syntax of type theory directly. And we can state that with a proposition, which is, so take T to be the type theory given just by the structural rules, then the syntactic category of T, which is built out of its context and so on in the way that we along the lines of this intuitive motivation, is then this is initial in the category of strict comprehension categories. This is, however, an extraordinarily vacuous theorem, because of course when you've just got the structural rules, then you don't actually have anything at all, any types. So to make this, so this is still, it's not entirely vacuous, in that it's the germ from which we'll build stronger theorems. This is sort of the simplest trivial case of them. But we can also state this in a slightly less vacuous way. So we can also say any purely algebraic extension of that. So that's saying if we have, so we just add certain types and certain terms, we don't add general type constructors. We add individual types and terms, but not type constructors. So then it'll be initial in strict comprehension categories with appropriate types and terms honestly, I would say think of this theorem as its more vacuous version, because that's what we'll generalize as we go on.
Well, the vacuous version is entirely vacuous, because
Yes.
if it's just generated by structure roots, then it's empty.
Yes. It is entirely vacuous, but I want to see it as there is a family of theorems which in general are not vacuous, and then this is the smallest special case of that family. And so this special case is vacuous. I want to use it to illustrate the family, and so. And then in this setting we can give our first comparison between weak and strict models. That if C is any comprehension category, then there are two split comprehension categories we can associate canonically to it. Which I'll call C lower star and C lower bang. Each equivalent to C in a sense which I won't quite define here, but equivalent in a very reasonable sense of equivalence. Yes, actually, right. That's all that I want to sort of say here to sum it up. But how do we define these? So both C star and C bang, they have the same base category. Actually, let's just name the structure of this as C tie chi as usual. So they have the same base category. We don't change what the contexts are, but we slightly change what the types are in either case. Where's So a type in C star over some object gamma is a family. So for each, let's call it so it's a family for each map into gamma. We give a type AF in the sense, a type in the sense of the original comprehension category over gamma primed, such that and I guess and maps phi f from so if we have f and f primed, and we have commuting triangle with G, that indeed this is fg, then we have a map phi g from a fg to a f over G, and it's a Cartesian map which is saying that AFG is some reindexing of AF along G, so it's some reasonable choice one might make for the reindexing, the pullback of this type along there, and also with phi GH is phi G, phi H. The identity is the identity. So what is this day adding up to? This is saying that this isn't, it's not just a type over gamma. It will have a type over gamma in there, because we can look at the case of F being the identity map, so that'll give us a type over gamma. And also, for anything we could reindex along, for anything we could substitute along, we get a choice of the reindexing, and these choices are strictly functorial. So a type here is a type together with a strictly functorial choice of all the reindexings that you could make any time you want to reindex it. And so now, think about how you reindex these. Anytime you try to reindex, you use the one that was chosen, and then for further reindexings, well, you again will have choices to make from the original family, and this will be strictly functorial because the family is set up to be. So, so the rest of the structure is exercise for the listener, or there are. It's in the various papers. So the main thing to think about is what the types are in each of these cases. Since they're supposed to be equivalent to C, the morphisms between types and the comprehension are all kind of determined as soon as you start thinking how it ought to be determined. They're all kind of determined by saying, well, they're basically the same as the morphisms or the comprehension in C. So then on the other hand, a type in C bang is sort of the opposite. This is the kind of think ahead strictification. It's saying you've already made the choices of all the reindexings you're going to do. This one is a procrastinator strictification. This is where you say you never actually do a reindexing. A type is so it's a triple over it's triple where we have VA, EA, and the name of A, where these fit together that VA is another context, EA is some type over VA, and then we think of this as a stand-in for what we get if we actually reindex this to gamma. So one way to see this is as a sort of a type that we're planning to do a substitution in, but we hold it as a delayed substitution and don't perform that. And another way to think of it is as a bit like a universe. So another construction one sometimes considers, which I won't go into detail, but it's the one that for instance, Vladimir uses for the simplicial model, is that you take types to be specified by maps into a universe. Could be a universal set or a universal simplicial sets or something. And then you have a canonical fibration over the universe, and you think of any map into the universe as representing the pullback of that fibration. Your universe is a sort of set of all small sets, and a map into it picks out for each thing over here the actual set that is named by that, which is the pullback of that fibration. And so this is as a sort of surrogate for that reindexing, but it's not a single universe. Each type can have its own different universe, VA and EA. We don't fix one universe for all time. The different types could be maps into different universes. And reindexing now is, again, so this way too gets to be strictly functorial because well, if you've got some map into gamma, you can just compose with that. You never change the VA, EA part, and so the bit which is an object and doesn't have a good equality to talk about, you don't have to talk about. The only thing that changes when you reindex is this substitution part, which is an arrow, and so there it's, again, composition is strictly associative, there's no upward-morphism to worry about. And so, this gives us, what I want to leave here. This gives us two ways of giving a split replacement for a comprehension category. So to start with, a comprehension category as a general, somewhat weak structure that does arise directly from the mathematical examples where you want to model the type theory, and comes out with something that's strict enough to directly model the type theory. But, as Vladimir said, this is a very vacuous type theory so far. So what we care about is when we can put logical structure on the type theory. So we can add constructors and things. So constructors in the type theory T correspond to extra algebraic structure on the comprehension categories. So the category of strict models of T will be comprehension categories with certain extra algebraic, or split comprehension categories with certain extra structure. So, so let's look at one concrete example. So binary sum types. So you've got the type theoretic rule, something like if got two types in the same context, then got a type A plus B, and then you've got intro rules. Then, so get together with something from A, you get the left-hand injection. Similarly for the right-hand injection. Then you have the elimination rule, which is you've got A and B as above, you've got some type C, the goal type dependent over the binary sum. We've got the marker running out. Are there any? Yes, there are more markers. So we've got the goal type that we're eliminating into. Can't draw the line yet, have more premises to go. So we've got the thing to do on the first component. We've got the thing to do on the second component similarly. Then we get the general eliminator, which I won't write out the full typing of, but this is roughly what it looks like, and we've also got the computation rule, which again, I'll leave the details of off for now. But so how will this look when we translate it into the language of comprehension categories? This is operations and equations that if we've got some gamma in C and A and B types over gamma, this goes to A plus B, except gamma was part of the data as well of this operation on the comprehension category. I should say operations on split comprehension category. And so, let's annotate this as an A plus superscript gamma B. And to get algebraic structure which really does model that, we have to add the extra condition that if we have f from gamma to gamma primed, then the pullback of the sum type should be literally equal on the nose to the sum over the new context of the two pulled back types. And similarly, we'll get terms for each of these operations giving terms which will commute strictly with the pulling back maps. And I won't, so for this case, I won't go into those in more detail, and we'll come back to those in a bit. So this we call strict stability. So this is, so if we've got this, we call this strictly stable sum types. And then the syntactic category of the type theory with sum types is initial among split comprehension categories, split comprehension categories with strictly stable sum types. And now this theorem is just as vacuous as the previous one, because of course sum types don't give you any base types to build out of. So this will still be an empty theory and a vacuous statement. But of course, you can see from this analogously how any other reasonable type constructors would translate similarly into strictly stable structure, into a certain algebraic structure that one asks to commute strictly with substitution in a split comprehension category. And so this theorem generalizes straight off to essentially any rules that we can write down for the type theory. They translate very naturally into to give a definition of strictly stable structure on a comprehension category, and then one always gets the analog of this theorem that the syntactic category of the type theory is strictly initial among split comprehension categories with strictly stable extra structure. And now at last that's a non-vacuous version of the theorem once you have enough interesting constructors in your type theory. But just like the functoriality was something which in nature is not often as strictly functorial as we like, similarly, this strict stability is something which rarely holds in nature. And so to find something which does hold in nature, we have to weaken this somehow. So this is, I shouldn't say very rare, but it's fairly rare in well done. So yes, so this is something which it holds in some examples, but certainly not in anywhere near all the examples you want. And we can see immediately, really, that it's a sort of mathematically slightly unnatural thing because it's talking about equality of things which will be objects. So, how can we weaken it to a more reasonable condition? So what... we look for weaker stability conditions. And one of the first things one might very reasonably think of, coming from a kind of categorical mindset, is that these equalities should be replaced by isomorphisms, or coherent isomorphisms in some sense. So, this will be what I'll call pseudo-stable sum types. Would be, so we have an operation for sums like before. So the pseudo and pseudo-stable should call to mind pseudo-functors and things from two-category theory, where pseudo tends to mean up to coherent isomorphisms. So if we've got, and again this now we want to think of not just on a split comprehension category, but on a general comprehension category. So if we have context and types over it, we can take their sum. And now when we have a substitution that we could make, then we don't get, when we compare the pullback of the sum to the sum of the pullbacks, let's keep a little more space, we don't get an equality, but we get an isomorphism, and more of these isomorphisms should be coherent, so again, phi of fg should be phi of f composed with phi g. This isn't quite true, we need to pull one of them back. And which one is it? I think it should be f star of phi g, something like this, possibly with the star function. We have the obvious equation saying that these compose right when you think about it. And now we also have to say something a bit new about the operations corresponding to the term formers. We have to say that the inclusions, so the inclusions now look like maps from the type into the sum type, or equivalently we can say the same thing in terms of context, to map over gamma from there to there. And now these, we could do these and then pull back, or pull back and then do these. And so now we've got something that we could ask to commute with the phis, and then similarly the output of the case operation, the output of the eliminator, should also commute with these coherence isomorphisms. And this is categorically a very natural definition, and it works very nicely, and this was, I think, one of the sources of what as far as I know is the first general coherence theorem for dependent type theory, which is so state in this language, if you've got if C is a comprehension category with pseudostable structure for some types or for whatever other types you might put into it, then this lifts to strictly stable structure on the right adjoint strictification C star. So on this strictification that we go over here, where a type came with all its choices of pullbacks. And pseudostability seems to be pretty much exactly what one needs to lift logical constructions from the base to the C star strictification. And let's see, for this to be useful, we need to be able to get some pseudo-stable structure. And one can often get pseudo-stable structure. The most notable case, and the one for which Hofmann originally proved this, was locally Cartesian closed categories have strictly stable structure corresponding to the constructors of extensional type theory. But one can actually say a slightly stronger thing, that this definition isn't really restricted to any particular rules or constructors one might think of. One can generalize this very naturally at a kind of fairly fine granularity, the granularity of individual rules and constructors. One can so any natural rule you could write down for the type theory, you can translate to a pseudo-stable version, and this theorem will go through. And the thing which then tells you when you can get pseudo-stable structure is... Oh right, hang on, no, I can't say that yet because I haven't said the weakly stable. Sorry, I'm missing a definition of a hypothesis for this, getting ahead of myself. So, let's put a blank here to get back to in 5 minutes. Actually, no, let's fill it in a bit now and then leave a blank to fill in a bit more. Certainly, for locally Cartesian closed categories, which are models of extensional type theory, but the place where this breaks down very frustratingly is in the homotopical models that not so. In, for instance, a simplicial set model, you don't get this, or at least no one has figured out how to get this for the simplicial model. What's the trouble? So, the first first thing which seems like it might be trouble is that in intensional type theory, the type formers are determined only up to equivalence, not up to strict definitional isomorphism. So one doesn't really expect automatically that these pullbacks will can be shown to be isomorphic terribly easily. Actually though, it usually turns out that they are. So for instance, in the simplicial set model, we certainly can get coherence isomorphisms like these for our interpretations of all the constructors. And we can also get them to commute with these. And for most constructors, they'll commute, the elimination terms will commute with those isomorphisms. But for the identity types, and if you're going in the lines of the category of calculus of constructions, the eliminators of some other inductive families, the eliminators for identity types don't commute with these, and it's a pain in the leg to try and get them to commute. And maybe there could be a way to, but none of us have found a way yet. So, one can work a bit and get pseudostability for the first couple of rules, but it seems to be impossible to get the eliminators to be pseudo-stable for identity types in particular. So, one has to find a different approach for these models, and this is where Vladimir used universe as the simplicial set model, And Michael Warren and I kind of looked at it and tried to see if one could make it work without needing quite the full power of a universe. And that was what led us to the local universes model. And so there, one certainly should expect still need some kind of stability condition. And what kind of stability condition does one need? One turns out to need what seems a very weak and probably a minimal stability condition to expect, that what we'll call weakly stable. Some types. And so this is a slightly fiddly state. So that if we're given something we'd like to take some type of, then data of A plus B and nu1 and nu2, call that a stable some type if for every f from gamma prime to gamma, so when we've got this, we then get pullbacks of all of these, and then for the elimination data, for the pullbacks of these things, so this is C and D1 and D2 corresponding to the rule there. There is some elimination section into the goal type. So what this is saying, it's essentially saying this thing, it's a sum type here in that we can choose eliminators, but we don't fix a particular choice in mind. And also whenever we pull it back, we can still choose eliminators for anything we're supposed to be able to eliminate into. And then we say that C has weakly stable sum types if every gamma and A and B has some stable sum type in this sense. And so this is now a pure existence condition. It's not about choosing any data, choosing any coherence isomorphism. It's not even about specifying particular choices of the stable sum types. Again, thinking constructively, we probably do want to have in mind certain ways of making the choices, but the condition, the stability, doesn't depend on what those choices were. So it's a pure existence condition, and it seems reasonable that this is a pretty minimal thing one might need, that one should need to be able to get a coherence theorem to work. That in terms of the stability conditions, if we're going to have a hope of interpreting logic in this structure, then any construction we make, if we're saying it's a sum type, it should still be something that can be used as a sum type that one can eliminate out of after one pulls back. And so then the coherence theorem here, it has the weaker stability condition. So if C has weakly stable structure, and this isn't a strict improvement on Hofmann's theorem, because this has an extra cost that you have to pay up front So you have to ask for certain products and exponentials in the base category. So there's a kind of extra cost that is paid up front here. But then once one has that, then, and this is sort of, the statement of this doesn't depend on what type theoretic structure we're considering. We set this up once and for all. And then any other structure that's weakly stable lifts to strictly stable structure on C-band. So this now does hold in this special set model and other homotopical models. And I think the thing to think of why in homotopical cases this is more reasonable to expect is that so in general, always equality on objects is a slightly unnatural thing to talk about. And the more that you kind of move towards a homotopical or higher categorical setting, the more then equality on morphisms is less natural to, maybe it's still okay to talk about, but one shouldn't expect so much to hold of it strongly. One shouldn't expect universal properties any more to produce on-the-nose unique morphisms so much. And so that's why the homotopical models need moving to this setting. I realise I'm a few minutes over. May I have 3 or 4 more minutes? I'll take 3 or 4, and I'll try not to make it more than 5. So, connecting the language of these two theorems now. The reason we can connect the language of these two theorems together and see why then this works in, for instance, extensional type theory and similar type theories, which is that if C has, or if C satisfies the reflection rule, or rather, sorry, I should say, if C has identity types,
If G or C.
C. So if C has structure corresponding to weakly stable identity types satisfying the reflection rule, then weakly stable structure corresponding to most of the standard type formers on C are automatically pseudostable. So this is because one can prove internally that sigma types and pi types and so on are unique up to equivalence. But if we have the reflection rule, that means that they're unique up to canonical definitional isomorphism, and those isomorphisms will witness pseudostability. And so this sort of shows us why for extensional type theory, it's extremely reasonable to expect pseudostability, and then we can apply this coherence theorem with the C star, but also then why it's not so surprising that when we don't have the reflection rule, we don't get the pseudostability so often, and we have to use some construction that takes slightly more effort to work with, like the universes or the C star strictification. And there's lots more I want to say, but I should stop there. Thank you.
I have a question. What about W types and what about universes?
W types play very nicely with all this. So W types absolutely fit straight into everything I've said without needing to kind of really make any twists. There's a slight subtlety in the definition of weakly stable W types because of the fact that they refer to pi types in their rules. So one has to sort of say something about how they play with the weakly stable pi types one's already assumed. But other than that, W types go through fine. Universes is more interesting. So the issue with universes is that they have type equality rules. Or that often when one sets up universes, one takes type equality rules. So for instance, saying that you've got a sum operation on the universe. If you've got two elements of the universe, you have their sum with another element of the universe. And now you have your elements, or T constructor, whatever you call it, of the elements of an element. The elements of a small type are an actual type. And one often asserts a rule, say for instance the original Martin Löf versions assert a rule saying that the elements of A plus B in the universe are literally equal to the elements of A plus the elements of B as an externally formed sum type. And so that's a rule whose conclusion is a type equality. And that plays badly with this construction in that it will almost never lift correctly. And I think it plays well with this construction, but I haven't, off the top of my head, I don't want to swear to that. But so I think that plays nicely with this construction. So for universes, if one wants to lift them using this construction, one has to weaken those rules which assert type equalities and replace them with rules which don't assert type equalities. Say, for instance, one natural candidate is giving structure saying that the elements of A plus B is again a sum type for the elements of A plus the elements of B, but it may not be equal to the specifically externally chosen sum type.
So I wonder if you can define a general notion of type former and prove your theorem once and for all. Is that?
Yes.
Yeah.
That's something that I and some others have thought a fair bit about, and I could talk for hours on ideas of the answer. For this paper, we sort of started out trying to think about it and then said, okay, no, this is beyond the scope of this paper. It would be a whole other question to go down. So that was what I was hinting at when I said that this definition clearly makes sense of the granularity of individual rules. This one, the way it's stated here, isn't down at the granularity of individual rules. It's done in groups. But it can, at the cost of becoming a bit more fiddly, it can be brought down to the granularity level of individual rules, and it makes sense for, again, any rules apart from those whose conclusions are type equalities. And heuristically, this seems to extend to any type formulas you can write down. Yes, as a heuristic I'd say I'd be reasonably confident that if you go away with your favourite type theory, write down the rules and try it, I'd be very surprised if this doesn't work. But I'd be pretty confident in stating, in saying it should extend without problems. This I'm hopeful it might, but I wouldn't want to say it could extend. I wouldn't want to constantly say it
doesn't really depend on the fact that these type formers follow this general pattern of introduction and elimination. It doesn't really depend on that.
No. So in the way we've grouped them here, we've taken advantage of that to sort of simplify it slightly compared to how one would have to do it for general individual rules, but one can give it for general individual rules. But this theorem, this one that gets the weakly stable structure to pseudo-stable, that does depend on the standard groupings and the fact that they determine all the structure involved up to uniqueness for term constructors and unique isomorphism for type constructors. You had a...
Sorry, a little question. I don't think you said explicitly, but presumably C goes to C star and C goes to C bang. Is that right adjoint and left adjoint? A forgetful thing from strong to weak?
Yes and no. At the level of federations over a fixed space, they are.
Yeah.
At the level of comprehension categories over a fixed space, C star is and C bang isn't quite anymore. And then at the level of comprehension categories with a logical structure, I think C star is, but there's a subtlety in that statement, which you can find the answers to in a paper by Curien, Garner and Hofmann recently. And for C bang, it absolutely isn't, and it isn't even functorial anymore when we have logical structure involved.
So,
Was that a sort of quick add-on to his question? Or
yeah,
a
so
question?
isn't C star and C, can you look at C star, for example, as the left-hand extension, some weak, like two bi-category form of left-hand extension of the identity, which would explain why you get that it's equivalent to C. I mean, that it really looks like that. And C bang is the right.
Let's see. So I'm not sure as basically the answer. There are similar things one can make. I would guess very probably. I've considered sort of similar statements, but I can't quite recall exactly what I checked and didn't work. Very probably.
Yeah, could you say a bit about what happens if we try not to work with Q-digits, but with arbitrary fibrations? To which extent can you still hope to strictify?
So, let's see. So most of these can, so not much of this, if you, right, so if you have, do you want the axiom of choice or not? If you want the axiom of choice, then the only difference is functoriality. If you don't want the axiom of choice, then you can really do very little of this without the cleaving. So the cleaving, I would say, the question with it isn't so much what can you do with or without it, but whether the functoriality of things is functorial in all maps or just in maps preserving the cleavings. And that's where the cleavings come in and play interestingly, in that, for instance, that the C star is at least up to the level of comprehension categories, and I think also up to the level of logical structure. It is functorial in general maps whether or not they preserve the cleaving. The C bang is, at the level of fibrations, it's still functorial in general maps. At the level of comprehension categories, it's only strictly functorial in maps that preserve the cleaving. Maps of comprehension categories that commute with the chosen cleavings. And similarly, at the level of things with logical structure, it's only functorial at all in maps that commute with choices of witnesses for the weakly stable conditions, which is sort of maps that have commute with way too much to ever really expect.
I think I need to call.
Thank you. Call it down.